Hello everyone. Let's solve two problems today. I know that it has been some time since I posted content on YouTube. So let's begin. So I have two problems from Irodov. Both of them are from mechanics. So I have a problem wherein I have been asked to find the acceleration of rod A and wedge B in the arrangement shown in the diagram below. I am going to show you the diagram. So this is the diagram wherein I have my rod A and I have this wedge B. Okay. I know that the ratio of the mass of the wedge to that of the rod equals N. Okay. Eta, sorry, not N, eta. And the friction between all contact surfaces is negligible. So this wedge is also standing on a frictionless surface. Okay. So essentially this is frictionless. And all the surfaces are frictionless. In fact, this surface is also frictionless. Okay. So given this condition wherein I know that the ratio of the mass of the wedge versus the rod is equal to eta. So let's assume that the mass of the rod is m. So the mass of the wedge would become eta times m. I have been given an angle of inclination for this wedge as alpha. Given all this information, I need to find out the acceleration of the rod and the acceleration of the wedge. Alright. So there are a few things which we will have to think about. Note that this rod is allowed to move only in the vertically downward direction, and this wedge is going to move in the rightward direction only. Okay. So why is that happening? Because this rod is kind of constrained to move only downwards because of this wall, right? So I have got two walls and the rod can move only downwards, and this horizontal surface, okay, it has constrained the wedge to move only in the horizontal direction. Okay, so let's assume that the rod moves down with an acceleration of AR and the wedge B moves down with an acceleration of AW, moves right with an acceleration of AW. Okay, now given this condition, let's write down a few equations. Okay, let me draw the FBD first. So if I draw the rod, let me draw in a better way. Yeah, so this is my rod, right? Okay, so there is its weight acting in the downward direction, which is going to be mg. There is going to be a normal force between the rod and the wedge, right? This normal force is going to act in this direction n, and there would be some horizontal forces which are essentially going to cancel each other out because this rod is not having any acceleration in the horizontal direction, so we are not going to consider that. Okay, and this rod has mass m, it moves down with an acceleration of AR. Now let's draw the FBD of my wedge. Alright, so I'll draw the wedge. Sorry, yeah. So this is my wedge. There is a normal force acting in this direction, and vertically it's not moving, so I'm not going to consider the vertical forces. Okay. Alright, under this condition, the wedge is moving in the horizontal direction, in the rightward direction, with an acceleration of AW. Okay, so let's write down some force equations. Okay, so the first equation would be mg. By the way, this angle is alpha, right? So if this angle is alpha, this angle is also going to be alpha, right? And this angle is alpha, which means that this angle is going to be alpha as well. Okay, all right. Yeah, so mg, I'm going to write down the force equation in the vertical direction, considering downwards as positive. Mg in the downward direction minus n times cos of alpha, minus n times cos of alpha because its direction is in the vertically upward direction. I have considered downward as positive. This will be equal to m into acceleration of the rod. This is going to be my first equation. Let's write down the force equation for the wedge. I'm going to consider the horizontal as positive. Okay, so this wedge, by the way, has a mass of eta times m. So n times this angle is 90 degree minus alpha, right? So n times cos of 90 degree minus alpha, that is sine of alpha. Sine of alpha is equal to eta times m into EW. This is my equation 2. Now I've got 3 unknowns and I've got just 2 equations, right? Which means that I'll have to figure out a third equation. Now what is going to be my third equation? It's going to come from a constraint. Now what is the constraint? This rod and this wedge are always going to be in contact, which means that the component of their individual accelerations along perpendicular to the incline is going to be the same. What I mean is, this AW is going to have 2 components, right? One is going to be perpendicular to the inclined plane, and this AR is going to have a component which is going to be perpendicular to the inclined plane. Okay, now perpendicular to the inclined plane, both these bodies are going to move with the same acceleration. Okay, so because they are in contact, they are always in contact. Therefore, this is a constraint. Both of them are constrained to move together, perpendicular to the inclined plane. Okay, so given that condition, this angle is alpha. So I can write AW into cos of 90 degree minus alpha, that is sine of alpha. Sine of alpha should be equal to AR into, this angle is alpha, right? AR into cos of alpha. Okay, so this is my third equation. Now I've got 3 equations and 3 unknowns. I can find out AR and AW. Okay, so what should be the first thing that I should be doing? Alrighty. Okay, so if I divide the first equation with the second equation, I get mg minus n cos of alpha divided by n sine of alpha is equal to, m gets cancelled, 1 by eta times AR divided by EW. Now AR divided by EW is nothing else but tan of alpha. Okay, alright, so this gives me some value of n, right? So if I try and solve against this, I get a few things. Mg times eta is equal to n into sine square alpha divided by cos of alpha plus eta into cos of alpha. Okay, is this the right way to solve this problem? I'll get a value of n. I can substitute that in the first and second equation to find out the result, but can I do something else? Okay, I think I have a better way. So I wouldn't divide the 2 equations. I'm going to do this. why find out the value of n if I can directly substitute that in terms of EW. Okay. Or maybe I think that's fine, whatever I was doing was fine. So from here I'll get a value of n, right? N will be nothing else but mg times eta into cos of alpha divided by sine square alpha plus eta times cos square alpha. Okay. Now if I've got the value of n, I can get the value of AW as n sine of alpha divided by eta times m. So that gives me the value of AW as mg into eta into cos of alpha into sine of alpha divided by eta times m, this eta times m into sine square alpha plus eta times cos square alpha. Okay, so eta m gets cancelled, so I get the value of AW as g sine alpha into cos of alpha divided by sine square alpha plus eta times cos square alpha. Okay, now if I divide the denominator by sine alpha into cos of alpha, or basically divide the numerator and denominator by sine of alpha into cos of alpha, I get the value of AW as g times g divided by what will it be, tan of alpha plus eta times cot of alpha. Okay, so this is the value of AW. If I've got the value of AW, I can get the value of AR as well, right? What is AR? AR is nothing else but AW times tan of alpha. Okay, so AR would be equal to AW times tan of alpha, which means that G tan of alpha divided by tan of alpha plus eta times cot of alpha. Okay, this can further be written as G divided by 1 plus eta times cot square alpha. Okay, so this is the value of AR. Okay, let me check the answer. Yeah. That's fine. That's perfect. Yeah. So this was the first problem wherein I had to write down the force equations and also one constraint equation. So yeah, let's solve the second problem now. So in this problem, I have been asked to find out the minimum acceleration with which bar A should be shifted horizontally to keep bodies 1 and 2 stationary relative to the bar. The masses of the bodies are equal. The coefficient of friction between the bar and the bodies is equal to K. The masses of the pulley and the threads are negligible, and the friction in the pulley is also absent. So I have this condition, right? I have a body, okay, and it's actually moving on a horizontal plane which is frictionless. Okay, all right. There is some coefficient of friction between this body and the two bodies. Let's call it A and B. Okay, and its value is equal to K. Okay, that's the coefficient of friction. So I've been asked to find out the minimum acceleration with which this bar A, so this is the bar A, sorry, this is not A, this is not B, this is bar A, okay, and I have to find out the minimum acceleration with which this bar A should be moved in the rightward direction so such that the two bodies, that is, let's call it body 1 and body 2, they are stationary with respect to this bar A. Okay, all right. So think of it this way. Let's assume that this body A was at rest initially. If it was at rest, this body, that is body 2, would have a tendency to move down. There wouldn't be any frictional force between the body 2 and body A. There could be some frictional force between the body 1 and body A, right? Because this body 1 would have a tendency to move in the rightward direction, right? Now, this body A is slowly forced to move in the rightward direction. Okay. Now, as we force it to move in the rightward direction with some acceleration, there would be some frictional force between the body A and mass 2, right? Body 2. And what would be the direction? Because this body 2 has a tendency to move in the downward direction, okay, the frictional force is going to be in the upward direction. Okay. This body also had a tendency to move in the rightward direction. So the frictional force on this body is going to be in the leftward direction. Okay. So as and when my value of A is increased, okay, the frictional force between the body 2 and body A is going to increase, and the frictional force between body 1 and body A would also increase. Okay. Well, if it is not moving, then it will reach a static value. Okay. Now, think about this. If both these two bodies are at rest with respect to body A, wherein body A is also moving in the rightward direction, okay, so these two bodies are at rest with respect to body A, but these two bodies will still have a tendency to move. Okay, so this body 1 will have a tendency to move in the rightward direction, okay, and this body will have a tendency to move in the downward direction, but it won't be actually able to move because of the forces, and that movement won't be possible with respect to body A, mind you. Okay, with respect to the ground frame of reference, these two bodies would be moving. Body 1 and body 2 would be moving, but with respect to this body A, these two bodies won't be moving. Okay, that is what has been mentioned in the question as well. Okay, all right. Also, I'm asked to find out the minimum acceleration, right? Which means that this body 2 would be interacting with body A in such a way that the frictional force between these two bodies is a static frictional force. Okay, and the frictional force between the body 1 and body A would also be static frictional force, because if my acceleration exceeds this value, both these bodies, that is body 1 and body 2, would have a tendency to move, and since they will have a tendency to move beyond the acceleration A, okay, these two bodies therefore will be experiencing static frictional force. Okay, so given that, let's draw the FBDs. Okay, so I have assumed that this body A is moving in the rightward direction with an acceleration of A. The body 2 will also be moving in the rightward direction only with an acceleration of A, and the body 1, that is here, will also be moving in the rightward direction only with acceleration A. Okay, because these bodies, that is body 1 and body 2, they are at rest with respect to body A. Okay, there is going to be some frictional force which is going to act in this direction on body 1. Its magnitude is going to be K times mg, it's the maximum static frictional force, and on body 2 the frictional force is going to be equal to k times the normal value. Now what is this normal value? It is actually the normal force which is driving this body 2 in the horizontal direction with an acceleration of a, right? So n has to be equal to m times a. Okay, all right. By the way, I have been given that the masses of the two bodies are the same, that is body 1 and body 2 is the same. So the frictional force effectively on body 2 turns out to be k times m into a. There would be some tension, right? So the tension on body A is T in the rightward direction, on body B it is T in the upward direction. Okay, all right. Given these FBD, let's write down the force equations. I'll write down T minus, this is for body 1, right? And I've considered horizontally rightwards as positive. T minus k times mg should be equal to m times a. Okay. And for body 2, the force equation would be something like this: T plus k times ma is equal to mg. This has to be ma, right? Yeah. Basically the tension plus the frictional force in the upward direction has to be equal to the weight of the body 2 in the downward direction. Okay. So with these two equations I have to find out the value of a. I've got two unknowns and two equations. I can easily find out the value of a. Alright. So this is my first equation. This is my second equation. What do I need to do? I just need to subtract the first equation from the second equation. So I'll write down k times m into a minus g, sorry, a plus g is equal to m times g minus a. Okay, m gets cancelled, so I get, what do I get? K equal to g minus a divided by g plus a, and if I apply componendo and dividendo, I get k plus 1 divided by k minus 1 is equal to 2 times g divided by minus 2 times a. Okay. This gives me the value of a as g times 1 minus k divided by 1 plus k. Okay. Yeah. So let me check the answer. Yeah. This is what my minimum acceleration should be for the body A, such that these two bodies, that is body 1 and body 2, don't move with respect to body A. Alright. So these are the two problems that I solved today. I'll try and come up with some more problems in the next class. Okay. Alright. Bye.